I am Dr. K. Misra. Welcome to my channel R Classes. R Classes is dedicated to uploading video tutorials on different topics of management and on different subjects. The video tutorials will be uploaded in due course of time. Currently, it is operations research, which you may call as quantitative techniques or quantitative techniques for managers, is going on. We have already uploaded video tutorials on CPM PERT, Simplex method and graphical method. Another aspect of linear programming problem that is very important, and that is transportation problem, that we are going to cover right now. Here the topics covered will be: what is transportation problem statement, solution to transportation problem, steps involved in transportation method, methods of obtaining initial feasible solution, methods of testing optimality of the solution obtained, special transportation problem. As we know that transportation is problem is basically related to the transportation cost. For any manufacturer in producing a product, it involves a cost, and that he decides the other different aspects of pricing, profit and all based on the total cost. Now the total cost includes cost of transportation also. At times it has been practically seen that the cost of transportation plays a major component, contributes major share to the total cost. So manufacturer is very much concerned about thinking of ways which can help him in reducing the transportation cost, so that the total cost of production per unit of a product is reduced. Taking this into account, this transportation problem has been considered, wherein transportation problem is basically a special type of linear programming problem that I had already explained it to you, as we did in case of graphical method or simplex method. So here in another special type of linear programming problem we deal with, which we may call as transportation problem. The term transportation is associated with determining the efficient transportation routes for shipment of items from factory locations to different warehouses or buyers' locations in the market area. Such problems which manufacturers face are known as transportation problems. The method to solve such problems is known as transportation method. Transportation is a OR technique intended to establish the least cost route of transportation of goods from the company's production location, that we may call as origins, to its warehouses, that is destinations located at different places. It is a special type of linear programming problem that involves transportation or physical distribution of goods and services from production points to the demand points. The problem involves determination of optimum routes to minimize shipping or transportation costs from supply sources to destination. As earlier I explained that typically the problem of a manufacturer. Say for example, there are three factory locations or production locations A1, A2, A3, where the supplies are available, and the manufacturer has to make the supplies to another 3 or n number of locations, wherein from each production point, say he has to supply the items to 3 or more than 3 n number of locations. And every route, say from A1 to B1, A1 to B2, A1 to Bn, or from A2 to B1, A2 to B2, or A2 to Bn, or from AM to B1, B2, etc., has got a definite cost element, and that cost element is per unit of item shipped through that route. Now, so these are the options available. Now, the manufacturer wants that this he should be, routing his items to such routes where he can minimize his total cost of transportation, so that the total cost of production can further be minimized. That's how that we can understand this transportation problem. Normally, we refer to, say, Cij, it is written here. So I number of origins, j number of destinations, Cij, that is cost per unit, rate at which the per unit of item is shipped, and Xij here is the I destination, origin to j destination, the per unit item to be shipped. Normally, we make an arrangement in matrix form that we will see in the further slides and more explanation. Now here we will talk about the problem statement. As earlier I was telling that this is a linear programming problem. One aspect of it we have seen, rather we can say the mathematical formulation that we have experienced in graphical and simplex method. The same method theoretically will also be applicable here. The classical transportation problem can be mathematically stated as below, assuming that the total quantity available at origins is precisely equal to the total amount required at destinations. Certain presumption is there that we need to have in our mind. We need to presume that whatever is being literally produced is subjected to be transported or to be supplied, or you can say whatever is being produced is exactly required at destinations. Presuming this, we can mathematically formulate here as minimum z is equal to summation I is equal to 1 to m, summation j is equal to 1 to n, xij, cij, subject to constraints, summation j is equal to 1 to n xij is equal to I, where I is equal to 1 to etc. m, summation I is equal to 1 to m xij is equal to bj, where j is equal to 1 to 3 up to n, and alternative solutions we must not be forgetting to write, that is xij greater than or equal to 0 for all I and j's, where ai, as earlier I referred to, the quantity of commodity available at origin I, here I may refer to 1, 2, 3, 4, whatever be the number of origins, bj, that is the quantity of commodity needed at destinations j, where j is further 1, 2, 3 up to n, and cij, cost of transporting one unit of commodity from origin I to destination j, and xij, quantity transportation from origin I to destination j. Now, as earlier I talked about, that the entire problem in that mathematical formulation may not be dealt with. Rather, here in a matrix form we normally represent it, where one side we take origin as a1, a2, a3, and row wise and column wise where it is written supply, that means the, so like a1, so at source a1 the supply availability, source a2 supply availability at source 2, A3 supply availability at source 3, and up to M, and the demand B1, B2, B3, Bj at different destinations 1, 2, 3. Typically, a transportation matrix is written in this form. When we will solve the mathematical problems, then you will come to know and you will be accustomed to writing the transportation model in a transportation tableau or matrix form, wherein the cost elements are written for each route, say C11, C12, C1n, etc. For source 2, C21, C22, C23, C2n, etc. So that's how the arrangement is made. We will talk about the further, matrix arrangement and then how to get the solution. But let me theoretically talk about that this particular transportation problem can also be expressed in terms of simplex method and also transportation method, of course, which we discussed earlier. So it can be theoretically expressed in terms of simplex method, where it is mentioned here minimum z is equal to x11 into c11 plus x12 into c12, etc., subject to constraints. Here you will see that destinations constraints and origins constraints are given, both are given. So actually this theoretically it can be explained, but practically it is not possible to solve transportation problem with the help of simplex method, wherein a number of variables involved, means the number of variables increases, and when the number of variables increases it becomes very difficult to find the values to all the variables. So just to theoretically define it is okay, but practically transportation method itself has got its own number of methods that we are going to discuss through next slides. Now again come back to this transportation method for which the chapter is intended to be discussed. We will talk about first the steps involved in transportation method. Only 3 steps here. In very easy terms I am telling you. First one, that we need to find the initial solution to a transportation problem. As I had already told you that the problem is arranged in a matrix form. There are 3 methods available: NWC, LCM, WAM. NWC here stands for northwest corner rule, LCM that is least cost method, and WAM, Vogels approximation method. These are 3 methods available. By any one of the 3 methods we can find initial solution. But the second is testing optimality of the solution found in at step 1. There are 2 methods available. One stepping stone method and another one is modified distribution method, in short known as MODI. And the third step is, if the solution is not optimal, revising the solution until an optimum solution is obtained. These are the only 3 steps that we consider in transportation method. But let me give you a caution here, that whenever we find initial solution with the help of NWC or LCM or Vogel's approximation method, so let me tell you that whatever solution we find with the help of NWC, that is slightly away from the optimal solution. If we try to find until and unless it is given that one must apply NWC, then you should apply. Otherwise, we should always go for finding initial solution only with the help of LCM or WAM, that is least cost method, that is nearer to the optimum solution, and Vogel's approximation method is very near to the optimum solution, so that it requires less number of iterations, means improvement, revision in the table, it is suggested that one should go for only VAM, that is Vogel's approximation method, and as far as optimality testing techniques are concerned, one should go for only modified distribution method, because stepping stone method at times it becomes very, it becomes very tricky one, because in every case we will come to see the method wherein we require looping of we require to form the loop for every empty cell in order to calculate the opportunity cost. So at times it may become cumbersome. That does not mean that it may not be applicable. Yes, it may be applicable, but here it is advised that one should go for VAM and MODI combination. As discussed, there are three methods available to find initial solution: northwest corner method, NWCM, least cost method, and Vogel's approximation method. Let us now go into detail. Northwest corner method. Step 1. Select the upper left northwest cell of the transportation matrix and allocate minimum of supply and demand, that is minimum A1 or V1 value in that cell. Number 2. If A1 is less than B1, then allocation made is equal to the supply available at the first source, that is A1 in first row, then move vertically down to cell 2-1. And if A1 is greater than B1, then allocation made is equal to demand of the first destination, B1 in first column, then move horizontally to the cell 1-2. If A1 is equal to B1, then allocate the value of A1 or B1 and then move to cell 2-2. Step 3. Continue the process until an allocation is made in the southeast corner cell of the transportation table. Having done it, then don't forget to come at step 4. Check the feasibility of the allocation itself, that should be equal to m plus n minus 1, and calculate the cost, where m, that is number of rows, n number of columns. If the number of allocations made is not equal to m plus n minus 1, the problem becomes degenerated. We remove degeneracy by allocating epsilon unit to the cell having least cost to make the allocation feasible. Here let me make it very clear that epsilon is just a symbol wherein it is highly negligible amount. It hardly has any weight, because so that it does not involve any transportation cost, and just to complete the number of allocation, make it feasible, we assign normally this epsilon to such a cell which has got it least cost, preferably 0 or slightly above 0 or preferably 0, so that it has hardly any impact on the overall solution. So that's how northwest corner rule we apply. Don't worry, we will show you that how to apply it by taking the practical problems in my coming up video tutorials. Now, least cost method. The step first is select the cell having lowest unit cost in the entire table and allocate the minimum of supply or demand values in that cell. In case the smallest unit cost is not unique, then select the cell where maximum allocation, that is allocation process will be the same as discussed before, can be made. Step 2. Then eliminate the row or column in which supply or demand is exhausted. If both the supply and demand values are same, either of the row or column can be eliminated. Step 3. Repeat the process with next lowest unit cost and continue until the entire available supply at various sources and demand at various destinations is satisfied. Again, don't forget to go to step 4. Must check the feasibility of the allocation, that must be satisfying m plus n minus 1, and calculate the cost. This is the complete explanation of least cost method. Will be shown to you by taking some practical example in the coming of video tutorials. Vogel's approximation method, most practical and applicable. Step 1. Calculate penalty for each row and column by taking the difference between the two smallest unit costs. 2. Select the row or column with the highest penalty and select the minimum unit cost of that row or column. Then allocate the minimum of supply or demand values in that cell. If there is a tie, then select the cell where maximum allocation could be made. Step 3. Adjust the supply and demand and eliminate the satisfied row or column. If a row and column are satisfied simultaneously, only one of them is eliminated and the other one is assigned a zero value. Any row or column having zero supply or demand cannot be used in calculating future penalties. Step 4. Repeat the process until all the supply sources and demand destinations are satisfied. Don't forget to go to step 5. Check the feasibility of the allocation and also calculate the cost. These are the simple steps of Vogels' approximation method. Don't worry, I'll give you practical detailing of it with the help of a practical example in coming up videos. Now come to most expected methods of testing optimality of the solution obtained by any of the three methods discussed a while ago. Once an initial solution is obtained, the next step is to check its optimality. An optimal solution is one where there is no other set of transportation routes, means allocations, that will further reduce the total cost. Thus, total transportation cost, thus we have to evaluate each unoccupied cell in the transportation table in terms of an opportunity cost of reducing total transportation cost. After obtaining the initial feasible solution, the next step is to check whether it is optimal or not. Here we have two methods to test the optimality. One is stepping stone method and another one is modified distribution method. Now let us talk about stepping stone method. Here SSM is detailed for calculating the opportunity costs. For all the empty cells, each empty cell is considered one by one. For each such cell, we find out as to what effect on the total cost would be if one unit is assigned to it. This we do by determining the closed loops taking one empty cell into account. Rules for loop formation given in the next slide. Steps involved here are: first, select an unoccupied cell, that is obviously non-basic variable. Beginning with a plus sign at this unoccupied cell, place alternate minus and plus signs to all the occupied cells in the loop. Keeping in view the shipment of one unit through the loop, calculate the improvement by adding together the unit cost figures. If calculated value is negative, this indicates that there is a chance of further reduction in the cost through this route and hence opportunity cost is positive. We do this for all unoccupied cells. We make maximum possible allocation to the cell having highest opportunity cost and improve the allocation further. Third, if the calculated value is positive, it indicates to negative opportunity cost. This iterative process is on till we get the optimal cost. Now here we'll discuss rules for loop formation. This is very important, friends. Just try to understand it, but don't worry, we will be taking up the practical problems in the following videos. But rules for loop formation is very important. First, an even number of at least 4 cells must participate in a closed loop, and an occupied cell can be considered only one and not more. Second, if there exists a basic feasible solution with m plus n minus 1 positive variables, then there would be one and only one closed loop for each cell. This is irrespective of the size of the matrix given. All cells that receive a plus or minus sign except the starting empty cell must be the occupied cells. The movement only horizontal or vertical on the path set by the loop is generally clockwise. No diagonal movement is allowed. Closed loops may or may not be square or rectangle in shape. In larger transportation tables, the closed loops may have a peculiar configurations and a loop may cross over itself. Now come to modified distribution method, or also it is termed as UB method. First, write the initial solution obtained by NWC, LCM or VAM. Check if it is degenerate. If yes, remove degeneracy as discussed earlier by assigning epsilon to required number of cells. Not only one, to required number of cells, it could be even more than one. If no, then second, add to the transportation table a column on the RHS titled UI and a row in the bottom of it labeled as VJ. Third, assign any value arbitrarily to a row or column variable UI or VJ. Generally, a value 0 is assigned to the first row, that is U1 is equal to 0. Fourth, consider every occupied cell in the first row individually and assign the column value Vj, which is such that the sum of the row and the column value is equal to the unit cost value in the occupied cell. With the help of these values, consider other occupied cells one by one and determine the appropriate value of UIs and VJs, taking in each case UI plus VJ should be equal to Cij. Thus, if UI is the row value of the ith row and Vj is the column value of the ith column and Cij is the unit cost of the cell in the ith row and jth column, then the row and column values are obtained using following equation: UI plus Vj is equal to Cij. Fifth, having determined all UI and Vj values, calculate for each unoccupied cell delta Ij is equal to UI plus Vj minus Cij. Delta Ij is basically here the opportunity cost. The delta Ij represents the opportunity cost of various cells. After obtaining the opportunity costs, proceed in the same way as in the stepping stone method. If all the empty cells have negative opportunity cost, the solution is optimal and unique. If some empty cells have the zero opportunity cost, but if one of the other empty cells have positive opportunity cost, then it implies that the given solution is optimal, but that is not unique. There exists other solution that would be as good as this solution. Now we will talk about some special problem. That was the end of the entire method. So let me conclude first before I go to the special transportation problem, that we normally should go for taking a VAM and MODI combination for solving a transportation problem until and unless it is intended to solve by any other method. Now come to a special transportation problem. Here are certain problems, cases where the transportation problems become a special one. Say first, unbalanced transportation problems. A transportation problem is said to be unbalanced where AI is not equal to Bj. That means the total supply should be equal to total demand. If it is not, then add dummy row or column as required to make the matrix arrangement satisfied and to make so that the problem can be balanced. Such dummy rows and columns always contain, say, zero cost. That's how we can make a problem balanced one. Second, problem with prohibited routes. In actual practice also, say that a manufacturer has to make supplies to 4-5 destinations through certain number of routes. Now he finds that due to some reason, maybe natural calamity, man-made created calamities, certain routes are blocked. Now he puts a condition that this particular item cannot be routed through this path. So that's how a restriction is put on such routes. What we do is that we try a very high positive value m so that it does not leave any impact on it, and then we solve the problem as discussed earlier with the methods. Third, unique versus multiple optimal solution. Herein, delta ig values, that is the opportunity cost, if negative for all the cells or some, then it is said that it is unique. But if some of the cells say having to be, having zeros, say for one, delta ig values is 0 for one or more than one, it indicates that this particular problem has many solutions and not only one. This earlier I had discussed. Degeneracy I also talked about, that the moment the number of allocations is not equal to m plus n minus 1, then we need to remove degeneracy. How do we do so? That we have already discussed. Another case is of maximization problem. So there is only one treatment for this maximization problem, is that we just reduce the all the elements. Like normally the maximization problem is basically a payoff matrix or payoff problem and not the cost related problem. So what we do is that we first take the maximum value of the table and we reduce rest of the units or the cost cell from that value. However, the maximization type problems, the transportation method is applied as in the case of minimization problem, except for the difference that in the first stage all the values of profit matrix are subtracted from the highest profit value in the matrix. That's what I told you, and rest the procedure remains the same. Theoretically, I have mentioned here also the dual of a transportation problem, though it hardly has much significance, but the way we wrote dual of a primal in case of simplex method or mathematical formulation, in the same fashion also it can be written here. So that is for only theoretical purposes in this slide that I may not include. So that was all about the entire process of transportation problem. For any queries, you can write to me at my email rclasses@gmail.com. Let me tell you that more video tutorials on quantitative techniques, operations research are available on my YouTube channel rclasses. Link is given here. So thank you for watching me. If you have liked it, so please like, share and subscribe the channel for your own benefit, for your own use. Thank you very much for watching me so patiently. Thank you.